Okay, we are recording. So you're asking about what sort of things will be on the exam. And I was thinking, I'm glad you asked, because I wanted to talk about that, because I think I've officially got enough material to put together an exam for next Friday. So if you want to take a look at the desktop camera here, I'm just wondering, is there a way for me as the host to pin another video, or do you just have to manually go to my other camera?
Each person has to manually pin it themselves.
So it's not the most elegant way. So I've just got my notes here. So I was just going to say exam 1, because there's varying degrees of difficult things I could ask, and I don't want to have you do like difficult coding exercises on the fly. So I was thinking about, like, you know, could I do like have you plot different cross sections of things? And I thought, no, I don't want you doing that kind of stuff. But there are going to be a few handful of sections here. We've done the parallel plate waveguide. Then we did, so I guess there was a bunch of little sub sections in the parallel plate waveguide, right? So you had the idea of the orthogonality between modes, orthogonality. We talked about the idea of the Fourier series between them. And there's mode cutoff. And then power are kind of the big topics. And after that, we did rectangular waveguides. And again, there was a TE and TM. As a general, for the exam, I'm probably going to kind of neglect the TM, because the ideas are mostly the same between them. You're just flip-flopping electric fields with magnetic fields. But I don't want to have to add that extra layer of confusion on top of things. There's not a whole lot of difference. And we've been focusing so much on TE anyway, so I will probably be strongly focused on the TE polarization for this stuff. So don't worry too much about TM, unless for some very basic stuff that will come later. But in terms of just things like calculating the power, I think we didn't even do power in the rectangular waveguide, because I didn't want to deal with that two-dimensional integral type stuff. We didn't quite get to that. But we did do cutoff. And the mode numbers and comment. So these are kind of the main things that we talked about. So you notice that we did a matching problem in the homework where you have to kind of identify the picture to the mode. And there was the circular waveguides. And that was TE and TM. So there may be a TM here because there's a slight little change in how you calculate the cutoff frequencies for some of those. So we're doing the TM case today. We'll review some of that. Again, you have cutoff is really the main thing we care about. We could have calculated power and things, but really it's just field profiles and cutoff frequencies are kind of the main themes in waveguide sections for most microwave engineering classes. And then finally, there was the microstrip, which we'll be doing Monday. Microstrip transmission lines. So you're going to do a lot of this stuff in your lab next week. In particular, I was thinking something very simple, which will be design a quarter wave transformer. So I'm going to have you do a homework problem on that. And I think that's one of the more practical take-home points from this section, is because microstrip lines are so ubiquitous and easy to manufacture that being able to do a simple design problem with that, I think, is definitely going to be a big exam question. So put a little asterisk on that. So you'll do your homework problem is going to have you do that. And I really like the idea of that's like the perfect exam question, because it's got a few basic ideas. It's relatively quick if you go through all the equations and you understand it. There's no horrible coding exercises you have to do, and that kind of stuff. So these are the main topics here. I will probably do one question from the parallel plate waveguides, where it's going to be one of those group questions, right? So here's some geometry. Now calculate the cutoff frequencies and the power flowing down it. I may or may not do some short thing with the rectangular waveguide, kind of like you saw with the matching. I'm a little undecided on that. Calculating the cutoff. This is a nice sort of interesting exercise involving the numerical use of Bessel functions. So something like that is a nice straightforward thing where it's just, here's a waveguide, calculate all the cutoff frequencies for TE and TM and tell me which one is the lowest. So that involves using that little basic skill. And then something with this. So that's like three nice little block questions, which should hopefully take up about an hour or less if you are paying attention to all the material. So we will be doing a lot of review on this next week. We will in particular do this Monday. We'll do this today. And then Wednesday will be available to just kind of go over a lot of the homework and answer any free questions along the way. So keep that in mind. So if there are no questions on that, we can jump ahead and do our practice problem today. So I'm going to go ahead and share my screen. And this is the perfect time to chime in with questions while I'm jumping between windows.
What's the finer definition between what a waveguide is and a transmission line?
That, I sort of wondered that myself, because they're sort of like the same thing, but they're treated a little differently. That's a pretty good philosophical question. I don't know if the book really has a solid answer on that either. Usually my gut answer to that, and you're welcome to challenge this later if you can find a better answer, but a transmission line would be something you would excite by attaching a voltage source to it and shooting charge down some conductors. That to me is a transmission line. A waveguide would be something that is excited purely by electromagnetic waves, not any sort of actual electrical connection to a signal generator. However, the fields that are generated once you do that are all sort of waveguides at the end of the day. But it seems to me that the TEM polarization, where both the electric and the magnetic field are transverse to the propagation, that feels like a good way to describe a pure, a transmission line as opposed to a pure waveguide. Does that feel like a good, I think that's the best answer I could give, because I think you're right. The book doesn't quite give the best discussion on that distinctions, and it's kind of, it feels like the two ideas are overlapping a bit, and in a sense there kind of is, because they both are sending energy in the form of these electromagnetic waves. So to reiterate that, yeah, go ahead.
I do find that as a satisfactory answer. How you excite the field in the waveguide does define the difference between a transmission line and a waveguide. Because a microstrip is kind of a unique case of a parallel plate. It's just,
yeah, that's a good way to think of it. It's like a parallel plate, only different. Because as you go higher in frequency, you'll get actually pure waves bouncing around in it. Whereas if you take an actual signal generator and touch that top line to the bottom, you're sending actual charges down the thing. And so both the electric and magnetic fields will be transverse to the propagation. So you have that idea of TE, TM, and then TEM. So I think that's the best way to draw that distinction. A transmission line will generally be a TEM field, whereas the other guys are going to imply TE or TM. So if you pop open your, Canvas, there's just practice problem we're going to do today. It should look very familiar. We're just doing the circular waveguide, only instead of TE polarization, we're going to do the TM. So to that end, we've got a waveguide radius is 2 centimeters. And we're just going to do that same thing where we want to calculate the first 5 cutoff frequencies. And I like this because the first 3, you can just do the table lookup in the book, but the last 2, you have to kind of do that graphical thing yourself. So if we pop this open, so you notice what I've done here. Oop, here we go. So I've created a little code. I'm going to put together this little script and I'll upload it. So don't feel like you have to absolutely follow along with it. But this is the exact same code we did Wednesday. I'm just going to tweak it for the TM case rather than the TE. So in particular, we start with waveguide radius. I just changed it to 2 centimeters instead of 1. And you still have to do that thing where we have to do that graphical plot with the Bessel functions. So remember on Wednesday, I said it felt a little backwards because the TE case is the harder one and the TM is actually easier, because for TE, instead of plotting the derivative of the Bessel function, you had to calculate the zeros of the regular Bessel function. So all you have to do is make that little change from calculating the derivative to just the regular Bessel functions. So we'll just calculate Bessel function for the 0 and 1 orders. So that 0 and 1 is your n, and then the m's correspond to the zeros in that thing. So you'll notice, I'm just going to change this to Jn rather than Jn prime. And now we have to do the same graphical thing. So instead of these p primes, we're going to calculate the p's. So do I need to review that basic principle real quick? So let's take a quick step back. We're just whip out the textbook real fast. So I'm going to show you the textbook. So this is my desktop, or sorry, my overhead webcam. So this is the way you calculate those cutoff wave numbers. So remember, for TE, that little p there had a prime on it, and it represented the zeros of the derivative of the Bessel function. Now it's going to represent just the zeros in the Bessel functions. So that is the boundary condition that is going to enforce no tangential electric field at the edge of the waveguide. Okay, so this is the thing. So once I know what these little cutoff wave numbers are, you can then calculate the cutoffs for the propagation constant, which in then will tell you the cutoff frequencies. So that little numerical number, that little term there, which we have to use numerical methods to dig it out, is the linchpin to this entire little exercise here. And then of course, these are the fields that we could have plotted after the fact. We're not going to focus too much on these because it starts getting extremely weird and wobbly to start plotting this stuff. So you saw the TM case where we could do that. And the TE is similar. You just have these blobs of energy bouncing around inside the waveguide. So of course, here is the table that you notice the first 3 are given, but we're gonna have to calculate the next 2 out here. So this will be a nice reference to make sure we're doing it correctly. So let's go ahead. I'm going to run the code. So here we go. So this is what we've got. So these are the Bessel functions of the first kind of order 0 and order 1. So each nth mode is going to correspond to a different order.
Can you share your screen?
Oh, sorry. God. Sorry, I'll like going back and forth. I always forget that. Thank you. So let's say that again. Here is the Bessel function of order 0 is the black curve. And you see how it does that kind of 1 over square root-ish decay on the envelope. I believe in the limit as you go to infinity, that envelope is a 1 over the square root of x, which corresponds to the electric field decay in polar coordinates, incidentally. And then this is the first order, n equals 1. So I believe they're unique in that the 0th one will always start here at 1, and then the rest all start at 0, which we can test just by checking them again, right? So there's number 2, and then if I put in like 5, you'll see how the red, it does this weird thing where it kind of flattens out in the middle, and then you see it kind of tapering off like that. So it's just a function. It has its own Taylor series expansion, and these are the weird behaviors, and a bunch of mathematicians have gone out of their way to study this. So you see, you go to 15, it wants to flatten off here and just keeps on going. So the 0, 1 is unique that it starts here at 1, but I believe all the rest will start there at 0. So hypothetically, you can just go out to as many modes as you want, but to keep it simple, we'll focus on the first 3. So here is the n equals 1 mode. So what we have to do now for our n equals 0 is we just care about these 0 crossings here. So there's a 1, 2, 3, 4, and 5 here. So you just dig out. And actually, some guy out there in the internet put together a MATLAB script where it will just calculate like the first 10,000 of these modes for you using a basic 0 finding. I've decided this is just more intuitive. We don't want to have to learn to use a whole unique code like that. Because this will work well enough to give you like 3 digits of precision. Whereas if you want some super accurate code, you can do a 0 finding algorithm that'll go out to like 10 decimal places or more. But this is usually good enough. So you notice it's 2.0484, which if we look in the textbook says 2.405. So there's our first 0 right there. So now we come back to our code. So I'm going to replace all of these PPs with just Ps, because originally I was saying P prime. So these are the 0 crossings of just the regular Bessel function. So we'll say 2.405, and now we have to replace all of these other guys. So I'm going to 0 them out so I don't lose my place. And now we go back. 1, 2, zoom on in. Just do a couple of zooms, and it's 5.520. 5.520. And if you're, again, you look at the book, 5520. So that's a nice little dummy check there. 1, 2, 3, like that. 8.654. 8.654. And again, that matches the book. And now for the next 2, we are on our own. The book will not save us. So we have to do the calculation. 1, 2, 3, 4. Zoom on in. So 11.792. Just like that. And then finally, the 5th one. 1, 2, 3, 4, 5. 14.931. Okay, so those were the zeros of the Bessel function of the first kind of order n. That was a bit of a mouthful there. So now we're going to repeat for the red curve of order 0. Let's see. Order 1 now. So you notice there is a 0 here, but that sets the, I think if you did that, k equals 0, you would get nothing but 0. So that corresponds to the trivial solution. So you can think of that as the 0th, m equals 0, 1, which we don't like. So we're going to skip up to here. And we get 3.832. And if we look at the book, yep, that corresponds to it. 1 and 2. And then we have 7.016. One, 2, 3. What are we at? 10.173-ish. Right? Well, the book says 174. Okay. And it's okay if that last little digit is off a smidge. You shouldn't need that much precision. 1, 2, 3, 4. So now we are on our own. We know we're doing this correctly. So we'll just zoom way in. 13.324. 24. And then finally, 1, 2, 3, 4, 5. So it's a little tedious, but you can see how it is pretty straightforward and that it just gives you an arbitrary degree of accuracy. 16.471, say. So those are the linchpin. Everything after that now, you just plug it into your cutoff frequency formula, which is your PNM divided by 2 pi A. And the book says 1 over the square root of mu epsilon, which is actually the speed of light here. So you can just slap your speed of light on top of that. And then we'll display those in units of gigahertz and see what we get. So let's do that again. So these are now the cutoff frequencies. You can see I've got 5.7 gigahertz, 13.16, 20, 28, and so on. So obviously, as you go higher in the mode number, you get higher cutoff frequencies associated with that mode. And it also tells us this mode here is our lowest cutoff. If I remember correctly, with the TE polarization, I think it was like one of the other ones was the actual lower frequency. Does that sound right? So it looks like we have the 1-0 mode is in fact the fundamental mode of the entire waveguide. So that's another important term. I don't know if I've emphasized that, but you often hear this idea of a fundamental mode, meaning what is the lowest cutoff frequency associated with this mode or with this waveguide. So no frequencies below this will propagate inside the waveguide, and you will in fact get an evanescent wave inside the circular waveguide. So that same argument applies that you'll get an imaginary component on your beta if you are doing a non-propagating mode. It's just that the mathematics in polar coordinates just get an extra layer of nightmarish. And it's tractable, you can do it, but definitely like for a class like this, that's way beyond the scope. But it is all there in the math and it can be done one way or another if you really need to know that information. So for now, this I think is a nice kind of balance of you understand the TE versus TM polarization. Can you find those zeros to tell me the cutoff frequencies of this waveguide? Okay. So those are our answers there. And you notice I only had to make a couple of little changes to the previous code to make that work. So we just replaced, instead of the derivatives of the Bessel function, we just had to find the zeros on the regular Bessel function. And of course, I could put a 2 here or a 3 or 4 and just keep going higher in n to see all those extra modes, but hopefully the idea is more or less settled by this point. I think that was most of what I had for today. We can jump a little bit ahead into Monday if there aren't any specific questions. Or if there is a homework problem giving people trouble, we can kind of look at that as well. I just barely posted it a couple days ago. So for example, we were talking earlier about how to recognize the different mode numbers. So one of your homework questions was a sort of a matching question. So where was that? I had rendering the profile. So good, this is a good kind of exam question, or may not work up to. But the question is, so, here is a electric field in a rectangular waveguide, right? So you see it is 0.5 centimeter vertically and 1 centimeter horizontally. And the question is, what mode are you looking at? Is this the n equals 1, 0, 2, 1, 4, 1, those sorts of things. So if you weren't here early, we were kind of talking about it, but the idea was you imagine just taking a cross section down the bottom here. And you notice the tangential electric field has to be 0. So when I look at the bottom of this thing at y equals 0, I can only see the y component of my electric field. So we'll go back here. So the page was 112. And so at y equals 0, let's take a look at the equations in the textbook. I'm going to pin that real quick. So this is on page 112. You notice at y equals 0, the Ex went to 0. No tangential electric field along that boundary. this cosine term goes to a constant. So you are basically just seeing this sine term when you let y equal 0. And by a similar argument, if I were to let x equal 0, then my tangential e sub y would become 0 because of the sine term here. And I would only be seeing this term here, this sine of n pi y over b. So the way you count which mode number you're looking at is just counting the peaks and valleys along those little profiles. So we'll go back to the screen share now. So you look at y equals 0. I'm only looking at the y component. You see it goes from 0 to a peak to 0. So one peak and no valleys implies n equals 1. And then, of course, if I go here, I see nothing. So that implies m equals 0, essentially, if it's constant. So then I can say something like, or sorry, I did that backwards. Don't confuse your m and your n. Right. So excuse me, let's do that again. We're looking at 1, 0. So there's one peak along the x here. So that is the sine of m pi x over a is what you're seeing here on the bottom. So if m equals 1, you get one peak. And then, of course, there is nothing here on this y. That implies n equals 0. Sorry, I had those m and n backwards there. So for example, if I let m equal 2 now, you'll notice I still have a 0 here on the left because n is 0. But my y component, I go from 0 to a peak because it's positive, and then a valley because they're negative. So that's a peak and a valley implies m equals 2. And I can do this, all the way out to like m equals 5, right? So you just count 1, 2, 3, 4, 5. And of course, a 0 that away. We can also flip-flop. I'm going to do 0, 3. So you see the same idea, it just rotated everything. And we're looking at the left edge now, where my y component is 0, and I only have an x component to my field. So these are my n's, goes to 1, 2, and 3. So that's very easy when one of them is 0 and the other is not. Oops. What happens if I do something like 2, 3? So now you get these two fields start just blasting into each other, but you can still kind of do that same argument, right? I'm looking at the left edge where I have set x equals 0. So all I am looking at is at x is 0, so there's only an e sub x component and is varying over y. So this will tell me n. N is 1, 2, 3 for this mode here. And you can also see the peaks aren't as strong down here on the bottom, but you can see how it goes 0, and then there's a peak, 0, and a valley. So m here is 2. So it goes 1, 2, even if you can't quite see. So that can make it a little more difficult just because the strength of the field is much weaker here on the bottom. So the amplitudes of your x and y components change depending on your mode numbers. But if you just count that difference, you can kind of see it. You notice you can maybe look at it here on this cross section. It's a little easier to see where there's one peak and then one valley. Or actually, because this is pointing down, you'd say that's a valley and then there's a peak. Same idea. Okay. So that is kind of how you recognize it. I probably won't do something. I could like go crazy, like 8 and 12, but that would just be so easy to lose count, right? It starts getting all pixelated and horrible. But you can kind of see the same idea. 1, 2, 3, 4, 5, 6, 7, 8. I just counted the little peaks in the blue there. It's a little hard to tell. And then of course I go Y, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n is 12 and m is 8. So just remember, m corresponds to the horizontal, n will correspond to the vertical. So that is how you answer the matching problem in your homework assignment. So we can go over another one. Are there any other questions there? Yeah?
Yeah, I just sent you an email because I think one of the homework questions is actually wrong.
Oh, what do you know which one?
Question 5 So on question 5, if you look at it, it should be m equals 2 and n equals 0, but you don't even give that as an option, right? Because if you go across the x, you would have the
it is very possible I mixed up the indices, because it's very easy to do that when you're trying to count your m's and your n's. So let's go ahead and I'm going to do the preview here. So here's the homework. You said question 5.
Yeah.
So this should be, oh, I think you're right. This should be 0, 2, shouldn't it? Not 2, 0. I might have.
It should be 2, 0, not 0, 2, right?
Yeah. So did that mark it wrong, or did it just not have the right one in there?
There isn't a 2, 0 in there.
Yeah. Okay. So I meant to say 2, 0, not 0, 2. So I can edit that real quick. Thank you for pointing that out. So let me just fix problem 5. So as you can see, it's very, very easy to mix and match those indices. Let's see. So there was, maybe we could go a little bit ahead to next week. I'm a little worried about doing a bit of signal stuff right before the weekend, but this is more of a conceptual thing. So let me make a note here. In fact, here, let's get out. So this is mostly about your labs, because one of the big problems I noticed with these nano VNAs is when we're doing TDR, you get this very sort of grainy picture of your impulse response, right? So we're going to do a little bit of signal processing to clean that up, because it turns out there is a way to get extremely high accuracy on the peak of that pulse to figure out exactly how long your cable might be, or perhaps to get a better measure of your propagation velocity. So I've got the overhead camera here, and I was putting together our labs here. So you notice I've got this little guy soldered here. This is a 50 ohm line. And the question is, what is the propagation velocity down this line? Because we have these approximate expressions we can do to get close enough answers. But we want to be able to verify those equations in practice. So let's just do a very simple little thought experiment here. Suppose I take my network analyzer and I measure this thing, and by exciting it with a perfect impulse response, right? So I turn on my voltage to 1 volt and I turn it off after like a picosecond. And that little pulse goes all the way down and then back again. What would I see in the time domain? So ideally, what you would see is something like this. So here is my time axis with presumably like nanoseconds here. This would be my reflected voltage as a function of t. And then there would be a little delta function right here, like that. So remember, the delta function isn't like a function per se. It's like infinitely tall in a sense with unit area. So they tend to represent that with like this thick arrow. And this would be some time t naught. Or if you could approximate it, as a pulse that you turned on for a very short duration and turned off again, you should see something maybe like that. But in an ideal signal processing sense, we would want to squish that pulse all the way down to 0 thickness with infinite height. So you can kind of think of it in both of those terms, and kind of a limiting capacity, and that's fine. So this is what we would expect to see, and that T naught would correspond to the round trip propagation here, right? So it's a 10 nanoseconds to go down and 10 nanoseconds to go back would tell me exactly how far it traveled if I knew the propagation velocity. So we don't actually measure the impulse response per se. When we do a measurement with the network analyzer, we're actually getting kind of like the Fourier transform of this thing, right? So that gamma of omega is actually a Fourier transform, ft. And this is a function of omega here. So if you look up the Fourier transform of a time-shifted pulse, you basically see something like this, where it goes, you get this kind of cosine term, right? And you can consult a Fourier transform table, but if I remember correctly, you get a cosine that just goes on forever. And technically there's a negative frequency that you'll want to associate with this as well, which would just be mirrored because of a real valued signal. But there's also an imaginary component, which is the sine doing something like this. Let's see if I can draw this. I didn't quite do that to scale. Like that. And the idea is this thing should have constant magnitude over all frequencies, assuming it's a lossless line or distortionless. And so that means these waves should hypothetically go on forever if I went out to infinite frequency. So that means this is the Fourier transform of this, and this is the inverse Fourier transform of that. So all of that sounds great in theory, but there is a snag when I do a measurement here with my nano VNA. And the obvious problem is my nano VNA goes all the way out to about here and just stops abruptly at 1.5 gigahertz, right? And then I don't know anything about this information here. In fact, for all practical purposes, it might as well just be 0, is what's essentially happened. So you imagine a rect pulse, and essentially, so let's do a little bit of some mathematics here. So I have gamma of omega. There's the true gamma, and then there's the measure. So I'm going to put prime. So prime is what I actually measure with my nano VNA. So it's going to be my true Fourier transform multiplied by a rect function with, I think you say omega over, I think that's how it works. So when omega equals omega naught, it turns on. So it's actually a 1 minus that. So it's going to be on and then it has to turn off like that. That sort of nasty thing. And if you want to be extra accurate, we have to sort of imagine this thing having a negative frequency. So a better way to visualize it, being just a little bit more mathematically rigorous, is you have this band limited window function like that. So here is my gamma prime of omega, and then there's my signal inside here doing this, doing that thing, and then of course the imaginary doing its thing like that. I can draw that by hand, and then abruptly turns to 0 for all these values after my bandwidth. So I'm going to write omega naught here like that. So you can think of it, at the end of the day, you're basically multiplying. So, oh, excuse me, I'm confusing rect with the step function. So yeah, it is exactly that. I'm sorry. Remember, the rect function has a value of 1 when you're inside this bandwidth, and then it turns off when you go beyond it. Sorry, I was confusing rect with step. Remember, the step function does this. The rect function does this. So I apologize if that was confusing. Oops, sorry. So that's a step function, that's a rect. So this is the guy here. I mixed it up with that. So sorry, to rein it all back in, my actual measurement on my nano VNA is this thing here. There's the true Fourier transform being multiplied by this rect function here. So what that implies when you do the inverse Fourier transform is my measured impulse response. I'm going to put a little prime on there. It's not a derivative, it's a measurement. It is going to be the true impulse response, and it's going to be convolved with a sinc function. So what you see in practice will actually look like the following. So I had this little time offset here, oops, excuse me, and instead of having that delta there, what you actually see is a little peak, and it wants to do this instead. Like that. So this is actually what you are kind of measuring when you take a band limited measurement of that with that nano VNA. However, there is one extra layer of squishiness on top of this that we have to account for. And that is here's my true Fourier transform, right? When I do this with the nano VNA, I'm not doing a continuous infinite many number of samples here. What you're actually doing is you are sampling it at discrete values. So I've got, you know, a point here and a point here and a point here, like this sort of thing. So there's 101 samples of this thing, both real and imaginary values here, like that. So when I have a bunch of samples of an otherwise continuous function, and I do the discrete Fourier transform, what you end up with in your time domain is something that might look like this. You get these samples doing this sort of thing. Right? And where they line up may or may not line up to any particular peaks and valleys, which means when you actually plot it in MATLAB, you see something like the following. You just see this sort of choppiness. That sort of makes sense. So it does this sort of thing. So you may have seen that on your nano VNA results. When you go through all that signal processing, you get this kind of discretely sampled version of something that wants to look like a sync pulse, but it is downsampled. I'm sorry, I didn't quite draw that very well. And depending on how coarse your sampling is, it looks pretty nasty and yucky. So what happens is this creates a problem where I can't really, it looks like my peak might actually be here in my sample data, when in reality, it might be kind of up over here a bit. So you have this problem of here is where I think my true peak is, or maybe it's there, but the actual true peak is here. So we saw how that seemed to introduce a lot of uncertainty in our lab measurements, and it was pretty bad, right? Because this was like almost, you know, half a nanosecond of time spacing, which corresponded to like a couple of centimeters of uncertainty when you tried to measure the length of something like this. So for the next lab, there is a very simple way to cheat this and recover that exact peak. One simple way is to do an interpolation and just do like a spline. There's also a kind of more intuitive way to think about it, is that when we do the nano VNA, we get a bunch of samples all the way up to here, and you have 101 samples, and then you stop. So what we're gonna do is draw that real quick. So this is all in the lab, but I wanted to walk through this just to kind of emphasize why this little method works. So what you'll have are a bunch of samples, and I'm just gonna sort of invent a bunch of samples like this. And so assume this is your reflection coefficient as measured by the nano VNA, and just bear with me a little bit and pretend that there's like 101 of these samples here, like that. So you have a bunch of samples in this array, and there's like n equals 101 of them. So, and then what's essentially happening is you have these walls here where everything is being zeroed off. So I have a bunch of samples out to some fixed bandwidth, say 1.5 gigahertz here, and then negative 1.5 gigahertz. And then it's just zero on forever after that. So the problem was we didn't actually include these zeros in our samples in our Fourier transform. We just sort of stopped right there. So the way you can cheat this is just pad your array with a bunch of zeros. Just like that. So you have this gamma. So when you actually write your MATLAB code, I have an array called gamma. And this thing is going to be a bunch of data with one, and it's going to be 1 by 101 samples. So all you have to do is something like take gamma, you're going to reassign it, and you're going to say gamma, comma, and you just slap a bunch of zeros on it. And you can add a gazillion zeros here if you want. In fact, I tried this. It went out to like 501 samples and it worked. So that just added 500 zeros out on my gamma term. So I haven't changed the information at all. I'm just adding more samples into the information that was already there. So when you take the inverse Fourier transform, you get a neat little effect. So I'm going to draw this out here. So originally, you would have a peak, a true peak that was maybe like right here, corresponding to this time offset. But when you looked at your samples, you tended to see something that maybe looked like this. So we'll do something like this. So when you play connect the dots with MATLAB, you see this peak getting sliced off the top. So it's hard to say where exactly is the peak of that pulse, because it may or may not land exactly on one of these samples. But when you do the zero padding, all that does is just add a bunch more samples. So you have this true envelope that's trying to do this, like that, sort of there. So by padding a bunch of zeros, it just added a bunch more samples, and you'll actually get a much more refined picture of where that peak is. Okay, so we're gonna do that trick in our next lab. And I wasn't sure, like, should I write an entire tutorial explaining the mathematics of that or not? But that's fundamentally all you have to do at the end of the day. We already have all this code that does all this processing. It's just before you do that inverse Fourier transform, you just gotta cram a bunch of zeros onto the edge of your gamma, and we'll effectively upsample this sinc function.
Now, using this trick, you haven't recovered any data that exists above 1.5 gigahertz. You've only
Correct.
increased the resolution of the output.
Yep, that's all you fundamentally did. As far as the Fourier transform is concerned, those zeros were already there. You just didn't sample them. That kind of makes sense. So what that does is essentially it artificially inflates your bandwidth all the way out to like, 10 gigahertz here. But you just are adding it with a bunch of zeros. So instead of getting, so it's as if you get that extra bandwidth, but it didn't change the fundamental structure of that little sinc pulse. It just sort of recovered some of the interpolation points between them in a weird sense. So it's a weird little trick where I didn't actually add any information, yet I was able to much better recover where my peak was in that little pulse. So that is a great way to get way awesome time resolution on your TDR, even though it's a band limited signal. And in fact, this is how a lot of TDR is done in practice, where I think, if you're familiar with Dr. Furs's work, I think their TDR is something like 96 megahertz, if that. That's their total bandwidth. And they just allow this thing to spread out to a huge uncertainty because all they care about is where is that peak. So it's this weird little trick where you don't need a ton of bandwidth to figure out exactly how far down that line is.
Wouldn't a spline be more computationally efficient and yield similar accuracy?
I did play with the spline, and you do get a similar result. The only hiccup on that is I think, I don't quote me on this, because there is a function in MATLAB called interp1, like that. I think it requires the signal processing toolbox. I don't know for sure. Because I don't know, because I have the university license that gives me all these toolboxes, and I never know if I'm using a forbidden function or not. But this will do. You can give it a spline interpolation. I tried it actually yesterday, and it did work. It just kind of plays a sort of parabolic curve fit with all these dots in the same sense. So in a way, that information is still kind of buried in there. So you can do an interpolation and get a similar result, which actually I think is how Dr. Furs's group does it, because you're basically like quintupling the number of samples you have to do in your Fourier transform. Or you can kind of cheat a little bit. This is a little, probably has a tiny bit of uncertainty and inaccuracy because you're trying to fit a parabola to a sinc, which may or may not have a smidge of error associated with that. Or it's amazingly accurate, and it's accurate enough for any practical application you want to do. But I like this explanation because it shows exactly how that information was still there, and you're recovering it using exactly the same code you've done before. The only change you have to add is this zero padding here. And then a little bit of extra bookkeeping after that to make sure all your arrays have the same length. So that I thought was a really cool trick because I was cracking my skull, like how do we increase our resolution on this TDR? And that's actually a very straightforward little way to do it because that peak there is the only thing we care about. That information is just sort of buried in between the samples. So using that, you can get very accurate measurements of the propagation velocity down this line. So for what it's worth, I got something like phase velocity is about 0.55 times the speed of light down this little strip line here. So we'll see what you guys get. You should hopefully get something very similar to that. And I believe, because I was kind of curious as well, a big problem with this microstrip line is what is the dielectric constant of this substrate? And I tried looking it up, and you don't really get an exact value. What you're told is epsilon r is probably like 4.2, but that's sort of like a guess, and depending on who manufactures the board and what their process is, it could actually have some uncertainty going as high as like 5.2 even. So this is more of a range of possible values it could be. So for what I got, it was probably more like 4.3 to 4.4 to correspond to this velocity of propagation. So I thought that's kind of a neat trick in that if you know what the velocity of propagation is, you can then reverse engineer what you think the dielectric constant is on this material. Because they will not specify it with a lot of precision. It depends on who made it and how they made it. But anyway, that's all the time we have. I went a little over. So I'm going to stop recording, but you're welcome to stick around and ask any questions if you have any.